Welcome to lesson 4.3. Today we're going to talk about the composition of solutions. There are a lot of different measurements we could use to indicate composition of solutions. You may see in other places, you may see things like weight volume and volume and percent and so on. We're going to look at the most common one that we use in chemistry, and that's molarity. So when two solutions are mixed, we can get a reaction to occur, and we can actually perform stoichiometric calculations with that. But anytime we did stoichiometry, if you'll recall, we had to know how many moles were in there first. And so we're going to use a concentration unit that indicates moles. So the concentration unit we're going to use is called molarity. It's often indicated with a capital M, and it's just used to express a concentration. So for example, a 2 molar solution would be more concentrated than a 1 molar solution. By definition, molarity is moles of solute, so the stuff that you're dissolving, divided by liters of solution, so the liters of the total mixture. So let's do a quick example here. Calculate the molarity of the solution in which a 184.6 milligram sample of potassium dichromate is dissolved in enough water to make 500 milliliters of solution. So first, I guess I thought that example was one that they were going to lead you through. So let's go ahead and let's see if we can get the answer they had. So first off, what we need to do is we need to figure out the molar mass of potassium dichromate. And so we're going to calculate that. So we have 2 potassiums, 2 chromiums, and then we have 7 oxygens. Oxygen has a mass of 16, and so if we multiply that out, we get 7 times 16, and we get 112. Chromium has a mass of 52, and we get 104 there. And then potassium has a mass of 39, and so we get 78 there. And so the mass of potassium dichromate is 78 plus 104 plus 112 gives us 294 grams per mole. Now notice it gives you milligrams in the prompt, so we do need to convert that to grams, and we're going to move our decimal over 3 places, and so we have 0.1846 grams of potassium dichromate. And if that just totally blew your mind, you might want to go back and look at metric conversions, because you're going to come across that again here in just a little bit. So now we need to convert that to moles, so 294 grams of potassium dichromate in 1 mole of potassium dichromate. So if we take 0.184 and we divide that by 294, we get a very small number, 0.0006255. Now that tells us how many moles we have, so we just calculated. And if you'll recall, molarity is moles of solute divided by liters of solution. So it tells us right here we have 500 milliliters of solution. Move the decimal, so we get liters 3 places, so we have that divided by 0.5 liters, and we end up with 1.25 times 10 to the negative 3rd molar. And let's see if that's the answer they gave us. Okay, they added an extra 5, probably rounding due to the molar mass. So, okay. All right, now let's move on. This one it does lead you through. Calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous hydrogen chloride in enough water to make 26.8 milliliters of solution. So we want to find the molarity. What do we know? We know how much hydrogen chloride gas we have. We also know how many milliliters of solution that we're making. What information do we need? We need to figure out how many moles of solute, and then we'll use the molarity equation. So if the molar mass of hydrogen chloride is 36.46 grams per mole, we're going to calculate out and figure out how many moles of hydrogen chloride we get. And then here is a dimensional analysis. Instead of just moving the decimal, it shows you mathematically what you're doing. And so there's our moles, and there's our liters. So we'll divide those two out, and we end up with what seems like, it seemed like we didn't have very much hydrogen chloride. We only had like 1.68 grams, but that makes a pretty concentrated solution of 1.6 molar hydrogen chloride. In this particular one, consider 5 solutions, each of which has the same mass of solute in 100 milliliters of solution. So we put in the same mass, whether it was 10 grams, 50 grams, 100 grams, whatever. Which one has the highest concentration? So in order to have the highest concentration, because you're putting in the same volume, it has to have the greatest number of moles. So if you're putting in the same mass, so same mass means the one with the smallest molar mass is going to be the one with the highest concentration, because you're putting in the same number of grams, and you're going to divide it by the molar mass, and so whichever one has the smallest number to divide by. And so let's look at some of these compounds. Potassium chloride, 39 and 35, 74 roughly. Sodium chloride, 23 and 35 is roughly 58. So we know that one's out. 2 sodiums would be 46, plus a sulfur would be 78, so we know that one's out. 23 and 19 would be 42, so we're down to that one. And then 2 chlorines would weigh about 70, so we know that one's out. And so our correct choice on that one's going to be sodium fluoride, because it has the smallest molar mass. And I can almost guarantee you questions like this are going to pop up on the test. So just reason through them conceptually. All you got to do is figure out the molar mass. You don't have to do several calculations. We can also manipulate the molarity equation. And so molarity is moles of solute over liters of solution. If we manipulate that, we can get that the moles of solute is equal to the liters of solution times the molarity. So basically what we did, molarity is moles over volume. And we just took moles times volume, and that gave, molarity times volume, and that gave us moles. So calculate the number of moles of chloride ions in 1.75 liters of 1 times 10 to the negative third molar zinc chloride. So just recall, zinc chloride, when it breaks down, is going to break down into 1 zinc plus 2 chloride ions. So keep that in mind. So moles is going to be equal to molarity times liters. Our molarity is 1 times 10 to the negative third. Our liters is 1.75. We multiply that out, and we get 0.00175 moles. But note that for every mole of zinc chloride, we get 2 moles of chloride ions, so we have to take that times 2. And so we end up with 0.0035 moles of chloride ions. Okay. So again, this is going to lead you through what I just did. And notice they rounded. Oh, actually, they did a little bit different. They figured out the molarity of chloride first, and then they took it times the liters of solution, and they ended up with the same answer. We just took it times 2 at the end. Which one of these has the greatest number of ions? Notice they're all 0.1 molar, but they have different volumes. So let's figure out first how many ions this is going to make. So this one's going to make 2, this one's going to make 3, that one's going to make 4, and this one is going to make 0 ions, because sucrose does not break down into ions. So this one is definitely out. And so what you would do here is you would take the molarity times the volume in liters. And then we need to take that times the number of ions. So 0.1 times 0.4 is 0.04 times 2 is 0.08. Now I'm going to take 0.1 times 0.3, so 0.03 times 3, I get 0.09. And this last one, I'm going to take 0.02 times 4, and I'm going to get 0.08. So the correct choice on this one is actually this middle one. This is an interesting question because it's one that you would utilize if you were studying anatomy and physiology, especially physiology. If you knew that typical blood serum was supposed to be about 0.14 molar sodium chloride, and you were to figure out how much sodium chloride you had and so on and so forth, then you could figure out backwards whether or not the body was operating based on that correct volume. So where are we going? We're going to find the volume of blood containing a milligram of sodium chloride. What do we know? We know what our molarity should be, and we also know that we're looking for the volume that has 1 milligram. So the information we need the number of moles in 1 milligram. So there's our molar mass. We're going to go from milligrams to grams here. We're going to divide by the molar mass. That's how many moles of sodium chloride we have. Then we're going to set that equal to so this is volume times molarity, and we're trying to figure out moles. So volumes are unknown. Here's molarity, just written a little bit differently. And then here's our number of moles that we just solved for. Divide that out, we end up needing 1.2 times 10 to the 4th liters of solution. So 0.12 milliliters of blood contains 1.7 times 10 to the negative 5th moles of sodium chloride, or 1 milligram of sodium chloride. When we work in a chemistry laboratory, a lot of times we'll have something called a standard solution. Like, for example, if we're diluting acids, we'll generally buy like a 12 molar hydrochloric acid. That's our standard, and we'll use that to make different dilutions. So occasionally, though, your standard will be something that you need to make in the lab, so perhaps you have a solid that you need to dissolve. And so what you'll do is you measure out the solid, you use the balance and measure out the specific amount of solid that you've calculated. You put this into what we call a volumetric flask. And this particular volumetric flask, I'm not sure what size it is, but this line here is the only volume marker that you have in this flask. And so what you're going to end up doing is you're going to making enough solution to go to that line. So let's say you need 500 milliliters of solution. You need a 500 milliliter vol flask. So you put your solid in there, you add water, you make sure it gets mixed. That's why we didn't add all the way to the line, because we want to get it mixed. And then we're going to add enough water to get it exactly to that line. And that's how we make a standard solution. To analyze the alcohol content of a certain wine, a chemist needs 1 liter of an aqueous 0.2 molar potassium dichromate solution. So we need to take a solid, we need to dissolve it, we need to get a 0.2 molar solution, but we need a whole liter of it. So how much solid must be weighed out to make this solution? So what are we trying to do? We're trying to figure out the mass of the potassium dichromate. What do we know? We know we need 1 liter of 0.2 molar. What information do we have? What do we need to find the mass? We need to know how many moles of potassium dichromate that is. So we're going to take molarity times volume. So there's molarity, again, written kind of funny, and then liters. So we need 0.2 moles of potassium dichromate. We're going to use the molar mass of potassium dichromate to figure out how many grams we need. So in order to make that 0.2 molar solution of potassium dichromate, we're going to have to first weigh out 58.8 grams of potassium dichromate. We're going to have to put that solute into a 1 liter volumetric flask, and we're going to have to add distilled water to the mark. Sometimes the solutions we make need to be prepped by dilution. So, for example, earlier I was talking about our acids. We generally buy those as 12 molar acids, and we a lot of times need to dilute those. So in that particular situation, it's actually a lot easier calculation because you don't need a molar mass. You only need to figure out how many moles of solute you have in order to dilute. When we dilute, we can use a few different things. We can use a volumetric flask. Actually, we will use a volumetric flask, same as we did in the last example when we're making the standards. But we also need a pipette, and so we can use two different types of pipettes. This one's a graduated pipette and measure out the volume there. Or we also have what we call a volumetric pipette. And volumetric pipettes are very much like volumetric flask. If I need 25 mils, I have to have a 25 mil volumetric pipette. I can't use a 10 mil volumetric pipette, or I can't use a 50 and figure out what that is. So I have a 16 molar solution of sulfuric acid. I want to prepare 1.5 liters of a 0.1 molar solution. So how do I do that? First, we need to find the volume of sulfuric acid required to prepare the solution. We know that we need 1.5 liters of 0.1 molar solution. We know that our standard, or our primary solution, is 16 molar. So we only need to know the moles of sulfuric acid in the required solution. So we want to make a 0.1 molar solution. We need 1.5 liters, so we need 0.15 moles. How much of the 16 molar solution do we need to get 0.15 moles? If we solve for V, we need 9.4 milliliters of solution. So in this particular instance, just a word of caution, if you ever have to dilute an acid, the saying is, do what you oughta, add acid to water. So that means don't take this 9.4 milliliters of solution, put it into your volumetric flask, and then add water to it, because it gets very hot very quickly. And so what you'll want to do is you'll want to add 200 or 300 milliliters of water, add this acid, and then mix before you keep adding more water, so you don't have a thermodynamic nightmare. Another method that you may have seen before is what we call M1 V1 equals M2 V2. And so if we go back to the other example we had 16 molar sulfuric acid. That was our M1. How much of it did we need? That's our V1. To make, I think it was 0.1 molar sulfuric acid solution, and we needed 1.5 liters of that. And so if you set that up and do the math, you'll still end up with the 9.4 milliliters that we ended up with before. So if we were going to prepare 2 liters of each of the following solutions, we have 1 molar sodium hydroxide. We want 2 liters of 0.25 molar. So what do we have? We have 1 molar. How much of it do we need? So there's M1 and V1. How much of it do we need to make a 0.25 molar, 2 liters of it? And that's in the prompt up there. So in order to do that, we are going to need 0.5 liters. And when it says describe how you would prepare, you would say that you're going to get a 2 liter flask, 2 liter vol flask. You're going to add 0.5 liters of your stock, and then dilute to 2 liters with water. So that's when it says to describe how you would prepare, you can't just stop with the math. You have to indicate how you're going to do it. Same thing here. We have a stock solution, so 1.75. How much of it do we need to make a 0.1 molar, and we want 2 liters of that? So 2 times 0.1 divided by 1.75, you need 0.114 liters, or you need 114 milliliters. So you're going to take 114 milliliters of stock, you're going to put that into your vol flask, and you're going to add enough water to get 2 liters. Okay. So 500 milliliters of 1 molar and 114 mils of the other. And this should be the last slide in here. Yep, it is. So 500 milliliters of 1 molar solution is diluted to 750 mils. So I have this solution right here, this solution right here, and all I did was dilute it to 750 mils. So what happens to the number of moles? So I haven't changed the number of guys in it. So let's say the ions are like little people in the army. all I did was increased the amount of water. So that means the number of moles stays the same. So that's what that M1V1 equals M2V2, because M times V gives you moles. So the moles before is going to equal the moles after. Okay. All right, that concludes lesson 4.3. We're going to start looking at chemical reactions, and we're going to move into the stoichiometry of chemical reactions after that.